Hello. So, we will continue our discussion on cloud computing. As in our previous lecture, we discussed about data store or data, how to manage data in cloud, having an overview of the things. Now, we would like to see that another programming paradigm which is called MapReduce, right, a very popular programming paradigm which is primarily developed by Google, but now being used for different scientific purposes. So, Google primarily developed it for their large scale search engines, primarily to search on huge amount of volumes of documents which the Google search engine churns, but it becomes an important paradigm, programming paradigm for this scientific world to work on, to exploit this philosophy to efficiently execute different type of for different type of scientific problems. So, MapReduce is programming model developed at Google. Primarily objective was to implement large scale search, text processing on massively scalable web data stored in using big table and GFS distributed file systems. So, as we have seen that big data and GFS distributed file systems, the data are stored. So, how to process this massively scalable web data, that means the huge volume of data are coming into play. Designed for processing and generating large volumes of data via massively parallel computation utilizing tens and thousands of processors at a time. So, I have a large pool of processors, a huge pool of data, and I want to do some analysis out of it. So, how can I do it? So, one very popular problem what we see is that if I have a huge volume of data and number of processors, then how to do, say, want to do some sort of a word counting or counting the frequency of some of the words in that huge volume of data. Like I want to find out that how many times IIT Kharagpur appears in this a huge chunk of data, which are primarily stored in this HDFS or GFS or big table type of architecture. So, and it should be fault tolerant, ensure progress of the computation even if the processor fails and network fails, right. So, because as there are huge number of processors and it is underlying network. So, and I do ensure fault tolerant. So, one of the example is Hadoop open source implementation of MapReduce developed at primarily Hadoop was initially developed as Yahoo and then became a open source, available in a pre-packaged AMIs on Amazon EC2 platform, right. So, what we are looking at is trying to give a programming provide a programming platform or programming paradigm which can interact with databases which are stored in this sort of cloud data stores, like it can be HDFS, GFS type of or managed by big table and so on and so forth. So, if we look at again parallel computing, as we have seen in our previous lectures. So, different models of parallel computing, it depends on the nature and evolution of the processor multiprocessor computer architecture. So, it is a shared memory model, distributed memory model. So, these are the two popular thing. So, parallel computing developed for computing intensive scientific tasks, as we all know, later found application in database arena or database paradigm also, right. So, it was initially it is more of a doing a huge scientific task, and later we have seen that it has a lot of application in the database domain too. And we have seen in our earlier lecture that we have three type of scenario. One is shared memory, shared disk and shared nothing, right. So, whenever we want to do a programming paradigm or work on something which can work on this sort of parallel programming paradigm where the data are stored in the different this sort of cloud storages. So, we need to take care of that how how what sort of mechanism is there, like whether it is shared memory, shared disk or shared nothing type of configuration. This is a picture already we have seen in our earlier lectures. So, we do not want to repeat. So, it is a shared memory structure, shared disk and shared nothing, but the perspective we are looking at now is little different. There it is more of the storage where we are looking at. Now, we are trying to look at that how the programming can exploit this type of structure. So, this is already a we have seen. So, shared memory suitable for servers with multiple CPUs, shared nothing cluster of independent server each with its own hard disk. So, connected by a high speed network, and shared disk. So, it is a hybrid architecture, independent server cluster, shared storage through high speed network storage like NAS or SAN. Clusters are connected to storage via standard Ethernet, fast fiber channel, infinity band and so on and so forth. So, whenever we do anything parallel or anything parallel computing or parallel storing and type of things, what is our back of the mind is to have efficiency, right. So, we want to do parallelism, to one of the major aspect is to have a efficiency. There may be other aspects of fault tolerant and foolproof and failure resistant and type of things, but primarily it should be efficient. Now, first of all the type of work we are doing, there should be inherent parallelism into it. If there is no inherent parallelism, then it may not be fruitful to do using always a parallel architecture. So, first of all there should be inherent parallelism, it should not be a sequence of operations and then you try to do a parallel. So, it is job 1, job 2, job 3, job 4, a sequence is there or in between some parallelism is there, but if you want to make a parallel operation that may not be good. So, if a task takes time t in a uniprocessor, it should take t by p if executed in the p processor. Ideally, if the parallelism is there and we are thinking that there is no cost in dividing, distributing and type of things. So, it ideally t by p is something ideal condition we can have. So, inefficiency is introduced in distributed computation due to need of synchronization among the processor. So, I need to synchronize among the processor. It is not like that the all processor have their individual clocks and you need to synchronize that where things will be there. Otherwise, if you divide the job into two and one executed now and one executed after couple of hours, then it could have been better that you execute in a one system. So, synchronization between the processors is one of the important aspect. So, need to synchronize. Overheads of managed communication between the processor is another aspect. Imbalance in the distribution of the work to the processor is another. So, it may not be equally divided and type of things. So, these are the different aspects which indirectly affect this efficiency or bring about inefficiency into this parallel implementation. So, parallel efficiency of an algorithm can be defined as T by P into T by P. So, if it is scalable, I say this is we say this is scalable or scalable parallel efficiency remains constant as the size of the data increase along with the corresponding increase of the processor. So, what is happening? More data is coming. So, you go on deploying more processor or you go on requesting from the cloud more processor and then your efficiency remains constant. The efficiency values does not change. So, then what we say that it is scalable. So, that if I increase both in the say for example, for linearly, then it goes on in the constant thing. Parallel efficiency increases with the size of the data for a fixed number of processor, right. It increases with the size of the data, and if it is a fixed number of processor, then we can have effectively more efficiency. Now, the example which is there in that book we are referring, also you will find this example in different literature, this sort of example, not the example. Consider a very large collection of document, say the web document crawled by the entire internet. So, it is a pretty large, it is large every day, it is growing. The problem is to determine the frequency, that is total number of occurrences of each word in this collection, right. So, I want to determine the total number of what is the frequency of occurrences of each word in this document D, right. So, thus if there are n documents and m distinct word, we used to determine m frequency 1 for each word, right. So, this is a simple problem, may be true or may be more relevant for search engines and type of things, right. So, we have two approaches. Let each processor compute the frequency for m by p words, right. So, each processors are, if there are p processors, if the m frequencies I need to calculate, I divide m by p so many. So, for example, I want to look for, I have 10 processor and I look, I am some 90 words, I am equal to 90. So, every processor does its chunk of 10, right, roughly. If I am if it is not divisible, then you have to make some as asymmetric division. So, it makes things, and at the end of things they again report the things together or in a some through some system. So, other way, let each processor compute the frequency of m words across n by p documents. So, total number of documents say 10,000. So, 10,000 number of words I am looking for 90, number of processor I am having 10. So, 1 is 90 by 10 is the 9 words on an average given to the every processor, and they count on the things. Other thing what we are telling, that each processor compute the frequency of all the 90 words, but on n by p document. If that 10,000 words and then p 10 processor, so on some 1000 documents. So, each take 1000 documents and do the processing, and once that frequency of these m words by individual processors come out, then I sum up this thing and aggregate and show the result, that this is the thing, right, by followed by all processors summing their results, right. Parallel computing, now which one will be efficient based on this parallel computing paradigm, we need to look at, right. So, parallel computing is implemented as distributed memory model with a shared disk, right. So, that each processor is able to access any document from the disk in parallel with no contention. So, this can be one of the implementation mechanisms. Now, time to read each word from the document, say let us assume that time to reach each word from the document equal to time to send the word to another processor via inter-process communication and equal to C. So, making things simple. So, it may be, it should be, means ideally in ideal case or in a real life case it will be different, but we make these scenarios. So, first approach, so time for so time to add to a running total of the frequency is negligible. So, summing up is negligible. Once I find the frequencies of this m word, then summing up is negligible. Each word occurs f time on the document on an average. So, if I, for our calculation sake, that each word as if word on an average occurs some f time, right. Time for compute all m frequencies with the single processor equal to, then I have n into m into f into c, right. So, this is the time to compute m frequencies with a single processor. So, if I have a single processor, this could have been it. So, if we do the first approach was this one, let each processor compute the frequency of m by p words. So, that is the first approach. So, each processor reads at most n into m by p into f times, right. So, parallel efficiency is calculated as nf fc by nf a p nm fc. So, 1 by p, very vanilla type considerations. So, we take that all are doing, all has more or less same frequencies, all are the negligible time for any aggregation, then the all time for means execute, means read and write and other operations we are considering C. Considering this, we are getting 1 by p. So, efficiency falls with increasing p. So, if we increase the p, then the efficiency falls, right. So, it is not constant. So, it is not scalable. It is one of the major problem is that though it is what we say easy to conceptualize and etc., but there is a problem in the scalability issue of the things. So, this one, that let each processor compute frequencies for n by m words, m by n words is not scalable. Whereas, in the second approach, where we that m words we divide into the different processors, or sorry, we divide that document D, whereas every processor computes this for all the m words and then aggregate. So, apparently what it looks that this could be more costly, right. So, it is there is aggregation thing, then you are doing clubbing those processor club means dividing the m set into different this whole document set into different partitions and doing that, this could be inefficient than the first one, but let us see what is there. So, the number of read performed for each processor is n by p into m into f, right. The time taken to read is n by p m into f, because you are having n by p amount of volume of the data, and then want to calculate for m into f into c. So, that number of time taken to calculate this read. Time taken to write partial frequency of m words in parallel to disk is m into c into m, right. So, once you are done, you need to write on the parallel to the disk, and that comes to be c into m. Time taken to communicate partial frequency, right, to p minus 1 processors, and then locally adding p sub vectors to generate 1 by p of the final m vector of frequencies, then what we have p into n by m by p into c. So, what you need to do? We are time taken to communicate partial frequencies, right, because you do not have the whole frequency. So, partial frequency by different processors and p minus 1 processor, and then locally adding p sub vectors to generate 1 by p of the final m vector frequencies is this one, right. So, individually need to do. So, if we add up all those things in case of this second approach, what we have this parallel frequency as this structure. So, 1 by 1 plus 2 p by n f. So, that is the if you look at it a little minutely, if you can consult the book, it is not a very difficult problem, difficult to deduce it. It is pretty easy, you just have to go by step by step. Now, there is an interesting phenomenon. So, the term we are having here is 1 plus 2 p by n m, right. So, in this case, if p is many times less than n f, right, efficiency of the second approach is higher than that of the first, right. Here, if it is p is many times less than n f, then this term this will be tending towards 1, and it can be seen that is much efficiency is much higher. In the first approach, so there is a typo, it should be read as in first approach, each processor is reading many words than it needs to read, resulting in wastage of time, right. What we have done in the first approach, this many processor we have divided this m into different chunk. So, the processor on a say as we have taken the example that if I am having m as 90 and number of processor is p. So, 90 by p is 10. So, everybody is getting 10, but when it is searching the whole document, so number of document is reading where there is no hit, right, it is no success. So, efficiency so in the second approach every read is useful, right, as it results in a computation and distributes to the final result. So, if for in the second approach every read is likely to be useful where it contribute to this result. So, it is scalable also. The efficiency remains constant at both n and p increases potentially proportionally. So, if what we see, what we have done there, that if my data load increases, I will increase the processor. So, if I proportionally increase the data processor, then my efficiency remains constant in this case, in the second case. Efficiency tends to 1 for fixed p and gradually increasing n, right. So, efficiency tends to 1 if the number of processor is fixed and gradually increased, we are increasing n, that means we are increasing the data load, number of processor fixed, and it will means it will basically approaches 1. So, with this context or with this background of that, which can be that this doing that individually, then aggregating is becoming more efficient. With these things, we look at that your MapReduce model, right. So, parallel, it is a parallel programming abstraction used by many different parallel applications which carry out large scale computation involving thousands of processors. Leverages a common underlying fault tolerant implementation, right. Two phase MapReduce map operation and a reduce operation, a configurable number of M mapper processor and R reducer processors are assigned to work on that problem. Computation is coordinated by a single master process. So, what we are having now, there are different mapper processors, like, and there is a different reducer processor. So, whole process I divide into two things, like I have a mapper. So, different mapper processors. So, there are M processor and there is reducer. So, there are different reducer processor. So, what it does, if when the data come here, it basically do some execution, and then this reducer maybe based on the type of problem, it will go on different reduce things and do the execution. So, reducer we generate is more of a aggregated result, right. So, what he tries to do, it is a parallel programming abstraction used by many parallel applications which carry out large scale computation involving thousands of processors. So, here the application come into play. So, it is a two phase process, one is a map operation, another is a reduce operation. So, that the configurable number of M mapper processor or reducer processor. So, it is configurable, that means you can have more etcetera mapper and reducer. So, MapReduce phase. So, if we look at the map phase, each mapper read approximately 1 by M of the input from the global file. So, it is a not the whole data D, but a chunk of the data are read. Map operation consists of transforming one set of key value pair to another set of key value pair. So, what map does? It is a one set of key value pair to another set of key value pair. So, map K1 V1 to K2 V2, right. So, each mapper writes computation and results in one file per reducer. So, what it does? It basically for every reducer it produces a file. So, it says that if there are reducer R1, R2, R3, a mapper Mi create 3 files based on the corresponding to the reducer. So, the files are sorted by a key and stored in a local file systems, right. The master keeps tracks of the location of this file. So, there is a master, MapReduce master, so which takes care of this location of the file. Each mapper produces a one file for every reducers, and the master takes care where the files are stored in the local disk, etc. In the reduce phase, the master informs the reducer where the partial computation have been stored or local file systems of respective mappers. So, that means, in the reducer phase, the reducer consult this master, which informs that where its related files are stored corresponding to the every mapper function. Reducer makes remote procedure calls to the mapper to fetch the file. So, reducer in turn make a remote procedure call for the mapper. So, mapper it is somewhere in the disk, and the reducer they may be in different structure with different type of VMs etc., running on the things. Ideally it is not far not geographically distributed, then the things will not work. So, nevertheless it is working on that particular data which are produced by the mapper. So, each reducer groups the results of the map step using the same key value function f etc. So, K2 V2 K2 f V2. So, here the aggregated function comes into play. In other sense, if we remember our problem, so what we do that every key or every word we want to calculate the frequency. So, the functional model is summing up the frequencies of the things. It can be different for different type of things. So, it does a K2 into V etc. So, it goes for another key value pair. Final results are written back to the GFS file system, Google file system, right. So, MapReduce example. So, if we see there are 3 mapper, 2 reducer. So, map function in our cases that is the data D, there are the set of word W1, W2, Wn, and it produce for every Wi the count of the things. How much count? The portion of the mapper it is having, right. So, every Wi it counts the thing. So, if you see if it D1 it has W1, W2, W4, D2 these are the things, and it counts this. So, every mapper does it, and then it basically stored in a intermediate space where the reducer reads. So, it generates every file for every reducer, like this particular things is generate a particular file for a reducer. So, there are 2 reducer. So, for 2 reducer every mapper generates the file. So, and the reducer in turns basically accumulate those. So, it says that it has the thing W1 and W2. So, W1 has 7, W2 has something 15, right. In this case W3, W4 are the other 2. So, the reducers reduces the things from the inputs of the or from the outputs of the mapper, getting the input from the mapper's output. So, MapReduce model is fault tolerant. There are different way to look at it. One is heartbeat message. So, every particular time period it says that whether it is alive and type of things. Communication exists, but no progress. Master, if there are communication exists, but no progress, master duplicate those tasks and assign the processor who are already completed or some free processor. If the mapper fails, the mapper reassigns a key value designated to it to another work node on the re-execution. So, if it is a failure, then it re-execute the thing. If the reducer fails, only the remaining tasks need to be reassigned to another node, since the completed tasks are already written back to the Google file systems. So, if the completed tasks are there, they are already in Google file systems, only the remaining tasks need to be reassigned. So, if we want to calculate the efficiency of the MapReduce, so the general computation task on a volume of data D, so takes WD time to uniprocessor, read time to read the disk from disk, performing computation, write back to the disk. Time to read write one word from to disk is C. Now, the computation task is decomposed into MapReduce stages like map stage, mapping time CM into D, data producing at output rho D, reduce stage reduce time CR rho D, and data produced at the output is sigma mu D. So, this is not that difficult. So, mapping time if how much that with the D every mapper is doing, data produced time is from the particular mapper, which is how much time it is producing, reducer's time and calculated with the every CR, and that finally we have that reducer output. So, considering no overheads in decomposing the task into map and reduce stages, we can have the following relationship, right. So, if we forget the overhead in decomposing in mapping and reducing, so we can have this summation of the things. Now, if you have P processor that serve as both mapper and reducer, right, irrespective of the phases to solve problems. So, the preprocessor sometimes it acts as a mapper, sometimes it acts as a reducer. Then we have additional overhead, each mapper writes to a local, we have some additional overhead writes to a local disk followed by each reducer remotely reading to the disk, right. For analysis purpose, time to read to a word locally or remotely, let us consider as same. Time to read a data from the disk is, for each mapper is W d by number of, if the number of processor is P, is W d by P. Data produced at each mapper is rho d by P. So, time required to write back to the disk, because once you read and you have to, after computation you have to write back to the T is that much. So, similarly, the data read by each reducer from its partition to each mapper, P mappers are rho d by P by P. So, rho d by P square. So, if we calculate like that, we say that the parallel efficiency of the MapReduce implementation comes as this one 1 by 1 plus 2 C by W into rho. Now, so this is the what we get a parallel efficiency out here. Now, if the indexing MapReduce, there are several type of applications. One is indexing a large collection of documents, right. So, that which is primarily one of the major motivation for Google. So, important aspect for web search as well as handling structured data. So, map task consists of emitting a Word document, record ID pair for the each word, like as we have seen W dk into W1 into n into map to, when it is map it W1 into every word dk. So, I can have a some sort of a indexing. Reduce step groups the pair of words and creates a entry into the thing. So, there are application in relational operation using MapReduce, right. Execute SQL statement, relational join, group by on large set of data, advantages of parallel database, large scale, fault tolerant we want to exploit, and I can have those type of function, like as we have seen that it is a group by clause and type of etcetera we can do. So, that some sort of a relational operations we can execute. So, with this we have a we come to this end of today's talk. So, what we try to do here to give you a overview of a MapReduce paradigm, that how a problem can be divided into a set of parallel executions, which is a mapper node which creates the intermediate results, and there is a set of reducer nodes which takes this data and create the final results, right. And what we can, which there are some of the things which is interesting, that the mapper creates data file for every reducer. So, it is the data is created per reducer. So, the reducer knows that where the data is there. Over and above, there is a master controller or the MapReduce master things which knows that where the data is stored by the mapper and how the reducer will read. Not only that, if the mapper node fails, how to reallocate the things. If the reducer node fails, how to reallocate, because the things or the reallocate the not executed data, not executed things, not executed yet to be executed operations and so on and so forth. So, with this we will stop our lecture today. Thank you.